Our paper addresses the problem of transfer between multiple tasks and multiple robots. We do this by decomposing policies into robot-specific modules and task-specific modules. We first create a module for each robot and each task. Every module is itself a small neural network. Given a particular robot performing a particular task, we form the policy by composing the relevant modules. This policy is a neural network that takes in observations and outputs actions. Our goal is to train modular policies on a subset of all possible robot task combinations such that the modules learned perform well in the remaining combinations without additional training. We refer to this as zero-shot performance. Given these robot task combinations to train on, we compose the appropriate modules to make 3 policies. Note that the modules of the same color have tied weights. We train the modules end-to-end using standard backpropagation. Given an unseen robot task combination, we assemble the relevant modules to form a new policy. Although each module is trained in other combinations, neither module has seen this particular combination before. We evaluate the zero-shot performance of this policy. To illustrate this method, we show the performance of modular policy networks for 3 scenarios in simulation. The first involves reaching for differently colored blocks. In this experiment, we have 3 robots, a 3-link robot, a modified 3-link robot, and a 4-link robot. We have 4 tasks, one corresponding to reaching for each of the 4 colored blocks, red, green, yellow, and black. Here's the set of all the robot task combinations that we train on. We test the zero-shot performance of the 4-link robot reaching for the black block after training on all other robot task combinations. This is the performance of the random policy. This is the performance when using the red task module instead of the black task module. Our method is able to perform the task zero-shot. The second scenario involves visually different manipulation tasks. In this experiment, we have the same 3 robots as before, and 3 tasks: reaching for a target, pushing a block, and inserting a peg. These tasks are both physically and visually different. Although the white block is present in both reaching and pushing, it represents the goal in the reaching task and the block in the pushing task. Similarly, the goal in peg insertion is black while the goal in reaching is white, making the tasks visually distinct. Here's the set of all the robot task combinations that we train on. We test zero-shot performance on the 4-link robot pushing the block, after training on all other robot task combinations. The goal of this task is to push the white block to the red target. This is the performance of the random policy. This is the performance of a policy which uses the reaching task module instead of the pushing task module. Our method is able to perform the task zero-shot. The third scenario involves more complicated manipulation tasks which do not use vision. In this experiment, we have 3 robots, a 3-link robot, a 4-link robot, and a 5-link robot. We have 3 tasks: pushing a block, pushing a drawer vertically, and pulling a drawer horizontally. These tasks involve distinctly different motions. Here's the set of all the robot task combinations that we train on. We test zero-shot performance on the 3-link robot pulling the drawer horizontally after training on all other robot task combinations. The goal of this task is to pull the gray drawer until its center lies over the red goal. This is the performance of the random policy. This is the performance of a policy which uses the vertical drawer task module instead of the horizontal drawer task module. The zero-shot performance of our method is close, but not entirely correct. To test whether these policies are good initializations, we train them for several iterations without strong reward shaping. The randomly initialized policy and the policy using the incorrect task modules are unable to learn to perform the task correctly due to delayed rewards. Our method is able to successfully perform the task in almost all situations.